everybody, welcome back to the channel and our first video into Unit 5, all about electrons. So this particular unit, there is a lot of very complex chemistry that is a part of this. However, we're really not going to focus on the complex stuff, but just so you know, there's a lot of deep chemistry that goes into all of this stuff. And we just kind of browse the surface of it. And I actually think it's really fun, though, to learn all about the electromagnetic spectrum and all about energy. And there's a lot of really cool labs and demonstrations we can do with this unit, demonstrations especially. So I'm excited for you to start to see a lot of that stuff, like our flame tests. It's always a lot of fun. Anyway, let's just dive right in. So we're going to talk all about radiation. And a lot of times when students hear the word radiation, or anybody, not just students, they always think that radiation is bad. Radiation makes you form into the Hulk. You're going to have this super strength and you're going to have 3 arms and all of this stuff. But actually visible light, so as you're looking at your screen and seeing the visible light from the screen and you go outside and it's a beautiful sunny day, that visible light from the sun is also a type of electromagnetic radiation. And electromagnetic radiation is not always bad. All it is, it's a form of energy that will exhibit wave-like behavior as it travels through space. So anything that behaves as a wave through space is a type of radiation. And really, there's a lot of different types of radiation. And you might be able to think of some types just, when I brought this topic up. Normally, one of the first one that pops up are X-rays. So X-rays are definitely a type of radiation. Not a very good type of radiation, but it's definitely on our list. And in fact, there are 7 different types of radiation. So there are radio waves, there's microwaves, there's infrared radiation, visible light, ultraviolet, X-rays, and gamma rays. Those are your 7 very basic types of electromagnetic radiation. And you are going to become very familiar with these 7 different types because in class, we are going to listen to the Electromagnetic Spectrum song. It gets the point across. You will know the electromagnetic spectrum. I have students who many years have passed by and for some reason this pops up in their life again and they'll message me and say, oh my God, that electromagnetic spectrum song helped me so much for this question I had for this test. And it's always really funny to hear that. So, and we call all of these different types of radiation, when we put them together, that's known as the electromagnetic spectrum. So radio waves all the way through gamma rays, we put this into a nice little chart and we call that chart the electromagnetic spectrum. It's really just the range of all the different types of radiation we can have. So what makes these radiation types differ from one another? What makes an X-ray different from a radio wave? Well, there's really 2 factors that make them differ from one another. And the first factor is your wavelength. And the wavelength is represented by the symbol lambda. And a lambda is an upside down Y. So I normally will draw this one first going sideways, and then I'll draw this one after that. And again, we call that a lambda. And your wavelength is the distance between corresponding points on adjacent waves. So basically, it's just how big the waves are. How far apart are the waves from one another? Corresponding points means the same point on adjacent waves, so waves that are right next to each other. How far apart are these waves? So again, we represent wavelength with this variable or unit lambda, and it's basically an upside down Y, and you say it just like this, lambda. And wavelength, so if you think all the way back to unit 1, where we talked about the different base units, the base unit for length is the meter. So because we're literally talking about the distance between waves, that's also going to be in units of meters. The word wavelength literally has that word length in it. So we're always going to measure wavelength in units of meters. Your second factor in what makes the waves differ from one another, these types of electromagnetic radiation, the second one is the frequency. And your frequency is how many waves pass through a point in a given period of time. So if you think about something that happens very frequently, maybe you go to McDonald's frequently, it's going to happen a lot. So if you have a wave that has a very high frequency, that means there's a lot of waves that are passing through a point in a given period of time. So a wave that has a low frequency, there's not going to be as many waves that pass through a point. The variable for this is going to be a nu, and it looks a lot like a V. However, this is a Greek letter nu. And the nu, I don't know if you remember doing this when you were little, but you might have drawn a house and then there was like a tree next door and you might have drawn the birds in the sky. Remember drawing the bird like with this kind of a weird V shape? I'm kind of making it out with the mouse here. That's kind of like a nu. So it's almost like this, like, it's a terrible example. It's almost like a curved V. So again, I'm going to draw this with the mouse here, and I'll draw this on the notes when we get to that point. But it looks kind of like this. It's just kind of curved. And units for frequency are in hertz or 1/seconds. They're the same exact unit. So hertz and 1/second is the same exact thing. So basically it's like saying how many waves are passing through a point in 1 second, the number of waves per second, hence 1/seconds. We also call that hertz. So here's just a wave. It really doesn't matter what it is because we'll just demonstrate these two different factors. So notice I have this right here that's labeled as one wavelength. So corresponding points means the same point. So in this case, it's just the top of one wave and then the top of the next wave. And it's adjacent wave, so it's right next to one another. So the distance between these two waves that are right next to each other, we call one wavelength. And you can literally measure that in units of meters or centimeters or kilometers, whatever it might be, even nanometers sometimes. So we call that a wavelength. Let's go ahead and just compare the frequency for these two types of waves. I think it's easier to compare the frequency or to look at the frequency when you have a wave with a high wavelength and a very low wavelength. So this top wave, of course, has a wavelength that's very, very short. So if I were to measure this distance right here, that wavelength is very small, especially relative to this wave on the bottom. So here's the top of one wave, and the distance to the next wave is very, very long. Let's just imagine that both of these waves are passing through a point in 1 second. If I notice this top wave that has the very low wavelength or the very short wavelength, there are a lot more waves that can pass through that given period of time. Therefore, the shorter the wavelength, the bigger the frequency. The shorter the wavelength, the more waves you can fit in a period of time, okay? As opposed to if we have a wave that has a very long wavelength, like this one on the bottom, the longer the wavelength means the lower the frequency. Not as many waves can pass through a point in a given period of time. So I like to think of this in terms of Lake Wallenpaupack. And I like to think of it on a very, not busy day on the lake, like in the middle of winter. And then I like to think of it on the busiest day on the lake, which is probably the 4th of July. Let's consider first when it's not a busy day on the lake. There's really no boats out. So if you're sitting on the dock and you have your feet in the water, the waves are very, very broad. And the reason why is because there's not a lot of waves on the lake. So if you have your feet in the water, you're going to have these really big ripples, these really big waves. And therefore, not as many waves are going to touch your toes in a given point of time. It's because the waves are so big. As opposed to if you're in that same spot on the lake on the 4th of July when all the boats are going out to watch the fireworks, it gets really, really, really wavy out there. And if you were to have your feet in the water, there would be a lot of waves that are hitting your feet. The frequency of those waves are increasing. Because the frequency is so high, the wavelength of those waves are so low. The waves are really close to each other. So therefore, the higher the frequency, the smaller the wavelength. And the lower the frequency, the higher the wavelength. So they're inversely proportional to one another. So in your notes, it might say a high frequency, low wavelength X-ray or gamma ray or something. You just want to write something like this down. And then the second one that might say, again, I'm guessing, I think this is what it says, a very high wavelength, low frequency radio wave. That would be like this one right here. So what relates these variables to one another? We just said when wavelength goes up, the frequency is going to go down and vice versa. We can mathematically relate these to one another, and we can do that using this equation. C equals lambda times nu. So the wavelength of a type of radiation multiplied by its frequency will equal C. And C is 3.00 times 10 to the 8th meters per second. And that is equal to the speed of light. Really, it's not just light, but all electromagnetic radiation travels at 3 times 10 to the 8th meters per second. So it's a pretty simple relationship between them. The wavelength times its frequency of any radiation equals 3 times 10 to the 8th meters per second. So there's another constant, unfortunately, that you have to remember. Let's do these 2 sample problems, and then we'll do some additional practice problems after that. All right, so before we go over sample problem 1, let's just talk about this equation one more time. So, of course, the frequency of a type of radiation and the wavelength of the type of radiation are inversely proportional. And for any type of radiation, we can calculate either one of those variables if we know the other one. And that's because the speed of light is equal to the wavelength times the frequency. So again, the frequency is kind of like a curvy V, kind of like the birds you would draw like over a house. So if there's the house, you draw the little door and you'd have the birds in the air. That's exactly what a nu was. So you didn't even know what you were drawing back then. And C is always equal to 3.00 times 10 to the 8th meters per second. And again, we call that the speed of light. But really, it's the speed that all radiation travels at, not just light. Although normally we don't say radiation travels at this speed, it's always light. So actually, if you were to take this as a conversion factor, 3 times 10 to the 8th, and use the distance away that the Earth is from the sun, you would calculate that the light that reaches the Earth is about 8 minutes old, which is kind of cool. It's just like a little fun fact for you. So once the light reaches the Earth, it's been traveling through space for about 8 minutes before it reaches us. So that's kind of neat. That's why we say something is light years away, is because it takes light so many years to get to the Earth, which again is kind of cool because if there was a supernova and like a star that's really far away, we wouldn't know till like many years later because we literally can't see. So when you're looking up at the sky at night, it's kind of like you're looking back in time because that light has taken years to get to the Earth. So it's like really kind of trippy to think about, like you're looking into a time capsule when you look into the sky. Anyway, just a couple of cool facts there for you. So C is the speed of light. That's this right here. And we know that this thing right here, this is our lambda, and lambda signifies the wavelength. Whereas this nu is the frequency. And again, frequency has units of 1/seconds or hertz, whereas wavelength literally has the word length in there, is in units of meters. And C is a constant, so it's always the same. So let's go ahead and try sample problem 1, knowing all of that. So we only have to use this equation. A certain blue light has a frequency of 6.91 times 10 to the 14th hertz. What is the wavelength of the light? So we're given the frequency, 6.91 times 10 to the 14th hertz. This right here is the frequency of the light. We want to know what is the wavelength. So that's what we're trying to find. So let's go ahead, and I'm just going to put a little lambda sign above this. That's what we're trying to find. So, and again, I always know C. C is always equal to 3 times 10 to the 8th meters per second. So if you want to, I sometimes like to make a list off to the side. So for example, I know frequency, 6.91 times 10 to the 14th hertz. I want to know the wavelength, and I know C, 3 times 10 to the 8th meters per second. Knowing that and this equation, let's just plug my variables in and solve. So C equals lambda times nu. C is 3 times 10 to the 8th. That's equal to the wavelength, which is what I'm trying to find. So I'm just going to leave that variable there. I'm going to put that in parentheses. And I'm going to multiply that by the frequency, which is what I'm given, 6.91 times 10 to the 14th hertz. So now to solve for this, this is no different than solving for the equation like 6 equals 2x. What is x, right? So in order to solve for that, you divide both sides by 2 and you get x equals 3. It's the same thing for this. The only thing that's different is you're working with exponents now. So it's really important that you use your parentheses when you are when you're plugging this in your calculator. So let's divide both sides by 6.91 times 10 to the 14th hertz. And you should get an answer of 4.34 times 10 to the negative 7th. Units are in meters because we found the wavelength. So wavelength must be in units of meters. Your calculator might have given you a number with a lot of zeros, so it might have been 0.000000434. That is the same thing as this. So this number that's on the screen is just represented in scientific notation. If you did not get this on your calculator, remember you need to use those parentheses. I can't stress that enough. So parenthesis around there, your division sign, and then a new set of parentheses around your second number. Let's go ahead and try B. A certain photon of light has a wavelength of 422 nanometers. So I have a wavelength here, 422 nanometers. Let's label this guy. What is the frequency of the light? What's the frequency? So we're trying to find the nu in this case. Let's go ahead and just make our list of our variables like last time. So I do have to use C equals lambda times nu. That's no shock because there's only one equation that we've been introduced to so far. Except there's another step here that we have to consider. Look, C is in units of meters per second. And my wavelength is in units of nanometers. So you have to convert nanometers to meters. And I'm sure a lot of you are rolling your eyes right now, but this is why converting was so important, is because you're not going to be given just one type of unit to just plug in and solve. A lot of times your values are in units that are different, that are your constants, and you have to account for that. So I'm not reteaching how to convert, because we did this back in Unit 1 and the videos are still up. So if you need help converting, by all means, go back to Unit 1 and watch the dimensional analysis video. That's what they're there for. And that's why I like these videos so much, is because you can just go back and watch them again. So I'm going to pick a different color here, but we have to convert nanometers to meters first. And if you look on your conversion paper, the one that I gave you in the very beginning of the year, 1 nanometer is equal to 1 times 10 to the negative 9th meters. So that is just that we know. You can look that up anywhere. So let's just convert nanometers to meters quick. So 422 nanometers, 1 nanometer, again, those units have to cancel, is equal to 1 times 10 to the negative 9th meters. And you should get an answer of 4.22 times 10 to the negative 7th meters. That's the number that I'm going to plug in to this equation right here. So let's just draw an arrow going up there. And I'm just going to rewrite that that value is equal to this one. So you needed to find that in order to use this equation. Now let's go ahead and plug everything in. So let's go back to this color again. So C, 3 times 10 to the 8th meters per second is equal to the wavelength in meters times the frequency. And just like before, not a difficult problem. It just looks difficult because you're working with lots of exponents and you're working with units, but it's the same thing like as solving this guy up here. And I know you know how to do that. So 4.22 times 10 to the negative 7th. When you solve for frequency, you should get 7.11 times 10 to the 14th. And units for frequency are hertz. And there's my final answer. So now that we've done those two problems, here's an actual electromagnetic spectrum. And as you'll see, radio waves are all the way on this side. And sometimes it differs. Electromagnetic spectrums are different depending on which one you look at. Some may have radio waves all the way on this side. It really doesn't matter. What you do need to notice, however, is that radio waves do have the longest wavelength. So right here, you have your radio waves. These ones can have wavelengths of about 1,000 meters. So that's like 10 football fields back to back. That's one wavelength of a radio wave. And these guys can go all the way down to a little bit bigger than a centimeter. So radio waves are really big, like football fields long. The higher the wavelength, though, the lower the frequency. So radio waves do have the lowest frequency. Microwaves are next, the second highest wavelength and with the second lowest frequency. And of course, as you go up, you see how the electromagnetic spectrum progresses. You have infrared radiation, then notice visible light comes after that. And what they're trying to show here is that this whole visible light region, they just kind of blew it up so you could see it a little bit better. And the reason why is because it's very useful to see the wavelength of a particular color in the units of nanometers. So it's easier to see like, oh, blue has a wavelength of about 450 nanometers just by looking at this. but that whole section right here fits in the visible light spectrum. And really notice how small visible light is. Most of the electromagnetic spectrum, that radiation, you can't see. Our eyes don't pick up radiation at all of those other wavelengths and frequencies. We just see Roy G. Biv. So radio waves, microwaves, infrared radiation, the first color in the visible light spectrum is red. Red, orange, yellow, green, blue, indigo, violet, and then ultraviolet comes after that. Then X-rays, then gamma rays. Gamma rays have your shortest wavelength, but your highest frequency. So just keep that in mind kind of as you're going through these. Let's finish those next 4 practice problems together. Sample problem 2. I'm going to do A and B, and then I'll put the answers up for C and D. So again, we're just using that one equation. So I'm just going to put these 2 up on the screen here. And let's go ahead and just write C equals lambda times nu. That's the only one we're going to have to use. A source of radiation has a frequency of 2.05 times 10 to the 14th hertz. That's our frequency. What is its wavelength? Wavelength's what we're trying to find. So again, if you want to make your list of variables, make your list. I'm going to stop the video here and make this list quick. So there's that list. If it's easier, if you like to look at it that way, if you like to highlight and put the variables above, it's up to you. There's a lot of different ways to approach word problems. So you kind of just have to find the way that kind of vibes with you the best. So let's go ahead and solve. C equals lambda times nu. Again, that's our only equation at this point. So 3 times 10 to the 8th meters per second is equal to wavelength, which is what I'm trying to find, times the frequency. To isolate the wavelength, let's go ahead and divide both sides by the frequency, and you should get a frequency of 1.46 times 10 to the negative 6th. Don't forget your units. Wavelength has units of meters. Now you can also figure out your units here, and I'm going to show you how to do that. And if you have no idea what I'm talking about, by all means, just skip this little section or pretend I'm not even talking about it. But I'm going to show you how to figure out what the units are, because in harder chemistry classes, a lot of times you might have to make sure your units work out. So the speed of light is in units of meters per second. And I'm dividing that by hertz. But remember, a hertz is the same thing as a 1/seconds. So my meters per second divided by 1/second. And when you were to, if you were to simplify this, you can't divide by a fraction. So instead you multiply by the reciprocal. And you see that you're actually left with units of meters, which is why we have meters left there. If you have no idea what I just said, then you just need to remember that wavelength is in units of meters, but this is why it's in units of meters. I always like to explain that just because some students like to know where the variables come from. Let's try B. A red light has a wavelength of 728 nanometers. Uh-oh. So looks like we have this guy in nanometers again, which again is quite common. What is the frequency of this light? What is the frequency of this light? Let's make the list of our variables here. Notice again, my wavelength is in nanometers, but C is in meters. You're not going to get this really clean canceling out of units if you don't convert nanometers to meters. So I'm going to pick a different color again. And first things first, we got to convert that nanometers to meters. Like I said, you're going to have a lot of, well, not a lot, but you're going to see you do have to convert a lot with nanometers to meters specifically in this section. So there's our conversion. and you should have 4.28 times 10 to the negative 7th meters. And again, that is equivalent to 428 nanometers. So that's what I just found up there. Now that I have that, you can use C equals lambda times nu. So again, let's plug our numbers in. 3.00 times 10 to the 8th is equal to your wavelength in meters, which is what you just found, times the frequency. Divide both sides by 4.28 times 10 to the negative 7th. And your answer is 7.01 times 10 to the 14th hertz. So what I'm going to do now is I'm going to do C and D, and these are actually just like A and B and the problems right before that. So I'm going to solve for these, and what I want you to do is you check your answers with mine when you're finished. Make sure you're actually giving these a shot and you're checking your work as you go along. And actually typing them in the calculator. I know some of you guys still have problems typing the numbers in the calculator, but if you're checking your work with mine as you go through, you would have specific questions for me the next class, or maybe you would catch a mistake because I might say a common mistake that students typically make. So make sure you're trying these on your own as well. Anyway, pause this video, try C and D, and I'll have the answers up here. And there's your two answers. So C, you should have 4.04 times 10 to the negative 7th meters. And for D, you should have 6 times 10 to the 16th hertz. So again, just double check your answers. Make sure you divided correctly. I also can't stress enough, write the work out. So many students try to rush to get these done, and rushing is not the way to go. Take the time, write the workout, try to understand what you're doing as you're doing it, because then it's going to make your life easier as you're going through it. You don't have to second guess yourself all the time. We're going to do lots more practice with this in class, so don't you worry. But otherwise, if you have any specific questions, make sure you jot a note down for yourself and you ask me in class. Otherwise, I will see you in the next video. Bye.